like Dr. Sirkovich said, I'm going to be presenting on my experiment, and that was the process of extracting and purifying beta amylase from a sweet potato. This is the paper that I followed for the procedure. I used it as my guideline. They're from India, and this is a little old. It's from 2001. Some of the goals of my research. The experiment itself is to isolate the enzyme beta amylase from sweet potato. And I was doing this so that the biochemistry students in the future could, I could use this and they could learn a little bit easier sort of the procedure for this lab. And while doing this, I would assay for maltose using starch as the ligand, and obviously beta amylase is the substrate. And I would also assay for proteins, and I just used the Bradford reagent just for specificity, I guess. Some background on beta amylase. It's pretty concentrated in sweet potato, but you could also find it in barley and soybean. This is beta amylase right here. You can see lots of alpha helixes. It's commonly used commercially to process starch and turn it into maltose, and maybe make like maltose syrup. That's artificial sweetener, or one form of it at least. It does this by taking starch and breaking off maltose molecules from either end. Up here is the starch formula. I guess that portion in the brackets is the repeating maltose structure, and it would break it off down, and that's what maltose looks like. It's just two glucose molecules. It's a dimer of glucose. So, all of my methods. It's going to get technical. So what I first did was peeled and cut and blended up the sweet potato using an immersion blender. I used buffer with this, so it would, throughout this whole lab I was using sodium acetate buffer, which has a pH of 4.8. I took this blended up mixture and centrifuged it so I could get rid of some of that unwanted potato tissue and tough skin. And then I discarded that. That's not what we were after. And then I took that supernatant with the enzyme in it and filtered it through some glass wool just to get out any really fine particles. And then this is what I call the crude homogenate, which is it's just the starting place. After that, I took some of that crude homogenate, that's what CH is. A very small amount, it's just what the procedure called for. This is the same ratios, I guess. I combine this with alginate, which is sort of like, it's a gelatin-like sort of powder. It ends up being a similar texture to gelatin. It's made from algae. And then I brought this to volume with some more buffer. This got agitated. This picture over here is what it would typically look like when I agitated. This is a vortex mixer. You would have a, this is my sample right there in the speaker, and I had it shaking on this machine. This got agitated so that the alginate could really bind to the enzyme, which is what we want. We want it to bind to the alginate so that we could actually extract it. And after that, I added a little bit of calcium chloride solution. This would make the alginate and hopefully the bound enzyme precipitate out of solution. This got agitated for a few more minutes and then centrifuged down. And the pellet ended up being like a really dense gelatin in texture. And after that, the pellet was resuspended in some maltose and left for 3 to 4 days to incubate, which was just in the fridge to keep it cold, and because my samples would go bad really fast if they weren't in a fridge. And what I mean by resuspended is just to kind of like mash the pellet up with maybe like a stirring rod in the tube so that the surface area would be increased a lot more. And what the maltose does is actually pulls the enzyme from that pellet into solution so that you can take the solution and analyze it. After the incubation with maltose, it was centrifuged again so that you could take the supernatant and analyze it. This is what I refer to as like dialyzed enzyme, or the paper calls it the E-loop. The dialyzed solution is after dialysis. And what the dialysis does is kind of pull the maltose out, because when you assay for the enzyme and it breaks up the starch into maltose, you could get a false positive if you actually have maltose in that solution. And this was left for 4, maybe 5 days with the buffer replaced 2 times throughout. And then that final E-loop was analyzed along with the crude homogenate and the supernatant, which is before adding maltose, because after maltose you could get a false positive, or you would actually. This is my maltose standard curve. This is just how I, after I analyzed for the actual enzyme, I could use this data to see if there was actually activity. There's just my, a maltose assay was done early on to get this without using actually any enzyme, and it was used with DNS reagent, which you see pretty commonly in chemistry. And it falls nicely on the trend line. And another standard curve, this one is for protein. Since the enzyme is a protein, this is how we assay for it. I did this using bovine serum albumin and Bradford reagent. And there aren't any error bars because we were running out of time and I could only do one trial, so that's why there aren't any error bars. So along the way I had several hiccups and like eureka moments, I guess. So first, one of the first things was my starch solution. Well, I made up all of my own solutions to use. And the starch solution had turned from a normal starchy white color to kind of a light blue, and that kind of let me know that it had been contaminated, and I had to make another one. The alginate solution appeared to be either moldy or contaminated, so we figured that some of the first assays I did weren't going exactly how they should, because a couple of the chemicals had something had gone wrong with them. When I was making up the calcium chloride, I made it at the wrong concentration. I think I made only 0.1 molar instead of 1 molar, which was a difference in how the pellet turned out. And throughout this, we kind of realized that the enzyme wasn't binding, most likely didn't bind correctly to the alginate. So let me take you through my results. We have our crude homogenate. This is just after blending and filtering. The supernatant, like I said, is after or before the incubation with maltose, which there actually shouldn't be enzyme here. This is your negative control. And this is my dialyzed. Should be really pure, but it turned out that we didn't get what we wanted. The volumes here, the 2.5 is what just was going in with the alginate. These other two were just my final volumes that I had collected The units of activity lets us know how much enzyme is actually there. And this is just per 1 unit is equal to 1 milligram of maltose liberated per minute. Liberated is just a fancy word for it took the enzyme off of the alginate and into solution. Or not off of the alginate, from starch into maltose. The total units are all of the enzyme should be found in the total volume. And the protein is also a measure of how we can assay for the enzyme. It's just in milligrams per mil, and then total protein is in milligrams. And then the specific activity is really the identifier, what it really boils down to. And this is in units of enzyme in milligrams to the negative first. This is the ratio of enzyme over protein, so it's not just any random protein, because that's how just assaying for protein might you could have other proteins in there too. And then the percent yield, this didn't work out because the units here for this, the total units I found for the crude homogenate was maybe 7 units, which is decently good. It's just basically straight from the potato. But the supernatant wasn't supposed to have any enzyme, and I found like a huge amount, and I double checked the calculations. So something really went wrong here. And the dilase enzyme or solution, we didn't find anything. Something went wrong. That's how we know it wasn't binding properly. And I couldn't calculate the percent yield because of this. Dr. Sirkovich sort of realized this himself. I wouldn't have, I don't think I would have picked up on this, but there was a specific product number of alginate in that initial paper that I showed you. And since it was about 20 years ago that the company Sigma Aldrich doesn't make that alginate anymore. So we just had to find a similar one. But this may be the problem, that it's a different alginate product. And this isn't by any means done. Any other future research student could pick up on this, could pick this up where I left off. So some of the problems or things that someone else could try for this experiment. The pH could be adjusted. We're not really sure if this is actually an issue, but it is just something to try. The assays could be sort of double-checked. This didn't seem like a huge problem, but still you could really refine it a little bit. You could conduct an SDS PAGE, which is just, if it's common in biochemistry to do this polyacrylamide gel electrophoresis, which really identifies for a molecule specifically in kilodaltons, if I'm saying that correctly. It could be the alginate, and this could be something to figure out in the future. And I just thought there would be a possibility to try a different method of agitation. There could be something wrong in the actual procedure. And this is just a paper from earlier.